Everyone, welcome back. So this is our first lecture in Chem 227, fall semester of 2023. The lecture is on methods of quantitation. Now, this presentation usually takes about 3 different lecture periods because I work with the students in real time, so I'm not just up there lecturing. I'm going about the room. We're solving problems together, and we go at the pace of the students in the groups that they're working in to solve these problems, and we come to some type of consensus before we move on, etc. And of course, there's also a day fully devoted to just working on problems where the TAs, LAs, and myself go around and assist students working on these problems. In addition, we also have workshops that we hold twice per week where students work in small groups with the TAs and LAs and myself to work on some additional, more complex problems than we can address in the lecture because they take a little bit longer. And so the students get a feel for how to approach these problems and what develop some strategies for essentially working through them, which a lot of it is essentially setting up workflows, because once you have the workflow set up, the math will fall out. So there aren't equations necessarily that you have to remember if you can think about the chemistry and the workflow that's taking place. Okay, I'm getting ready to share my screen. So again, we're probably going to get this done within 50, maybe up to 60 minutes, but this is a sequence of topics, methods of quantitation that would occur over 3 lecture periods and maybe even into a 4th one, depending on how fast we go. Okay, so I'm going to share my screen here and we'll get started. I'm going to hide my controls, whether you can see them or not. Okay, and we're going to start our slideshow. Okay, so when it comes to chemical analysis, there are 2 general approaches for conducting chemical analysis. One would be a targeted based. I know what I'm looking for, and so I'm going to essentially perform my sample prep with those specific chemical compounds in mind. So the sample preparative methods that I take to extract those analytes of interest into a matrix that's compatible with my instrument will be based on what I'm looking for, what I know I'm looking for, and the chemical properties of those analytes. And how I optimize my instrumentation will be configured in a specific way to look for those particular targeted based compounds. Okay, and so the opposite of that would be more of a discovery based. And so my sample preparative methods and my instrumental methods that I develop will be different than if they're targeted based. I give students an example of the shoe bomber, right, who had TATP in the shoe, got onto the airplane. He was able to get through the security systems at the airport. The ion mobility spectrometers are tuned for essentially explosive vapors, but not for TATP, at least not at that time. And so he was able to essentially go through security, even though he's being screened with an IMS, because the IMS was not configured to be looking for TATP. No one thought at that point in time that TATP might be an explosive that someone would use. And so he was able to get through. And so there's a real difference. And we'll show a figure a little bit later on as well, that we're setting up our sample preparative methods and our instrumental methods for either targeted based analysis or discovery based analysis. And there's not a lot of overlap. Okay, so if you're set up for targeted, you could miss chemicals that are there that are important or would be important to you if you knew that they were there, but you're not looking for it. And if you're doing discovery based, well, you're opening up your search parameters a little bit, and so it's very difficult to become quantitative at that point in time. And so you really have to know what your what type of analysis you want to perform so that you're optimizing for that particular set of analysis. Okay, so I don't get into this a lot with my students, but sampling is important here as a part of the chemical analysis. If I'm sampling tissue, blood, soil, air, water, I just need to make sure that whatever samples I collect from the source, that those samples are in fact representative of the source from which they come, right? Because many matrices are heterogeneous in nature, and so I want to make sure that whatever I sample is representative of the matrix of that particular material as a whole. So I want to perform some type of statistical sampling as well, because one sample, but if I mess up, I don't know that. So if I perform multiple, if I collect multiple samples, perform multiple analysis, I have a little bit better handle on whether there's a mistake, a random error or a systematic error that I've introduced into my sample preparation or chemical analysis. And also how to preserve samples as well. So if I'm an environmental geologist or environmental engineer, and I'm going out and sampling soil that's been contaminated with hydrocarbon residue, hydrocarbon residues have volatile and semi-volatile components associated with that contaminant. And so when I collect my sample, it may be 48 hours later before I actually perform the chemical analysis. Well, if I allow that sample to continuously outgas and volatilize, the concentrations of those chemicals will be different at the time of collection from when I analyze that particular sample. So I have to think about preservation of samples as well, right? And this is even related to doing blood alcohol analysis, right? Blood alcohol content changes as a function of time. So there are certain time constraints and methods of preservation of blood samples, et cetera, to ensure that you're measuring blood alcohol content as best you can at the time that the person was essentially stopped. Okay, so sample preparation as well as key to the type of matrix that you're trying to sample and the analyze that you're looking for, and of course the analysis as well. And then there's reporting and interpretation. So if we look at sample preparation, right, it's really going to be matrix dependent, analyte dependent, and instrument dependent, because there's interfering agents and masking agents and all sorts of things that can get in the way of a good method for determining accurate or as accurate as possible concentrations of an analytes of interest. Down below, the link to that paper is essentially something I thought was interesting in terms of an interfering compounding analysis of pharmaceutical syrups, in terms of it was interfering with the analysis that they were trying to perform for particular target analytes. And it really goes in there, right, that this is a common compound in these pharmaceutical preparations that can give you false positives or false negatives, or at least inaccurate results when it comes to quantitation of the target analytes. And so we have to think about these things. It's not just throw a sample into methanol and extract out an analyte and inject that into an instrument. There's a lot more thought that must be put in to these overall methods. And then method optimization validation, which is the instrumentation aspect of that as well. And this is just a result from a former graduate student of mine when we were essentially developing LC-MS methods for looking at antidepressants. And based on our MS parameters here, we have a false peak arise from dicipramine, just solely based on the instrumental method that we were setting up at this point in time. And so, it's looking at targeted versus discovery-based, and we're using a discovery-based protocol here for a sample that didn't contain dicipramine. But we're trying to develop a method overall for any antidepressants. But what we found is when we open up these search parameters a little bit on the LC-MS, that we would get these high false positive rates for dicipramine when it wasn't actually there, because we were using control samples. And so just at least highlighting the fact that if we're doing more targeted based analysis, that false positive peak goes away for dicipramine. But if we open up the search parameters, we can get it actually as a false positive. Okay, anyway, so sample preparation is probably the most crucial step in any analytical procedure. That's the limiting factor in chemical analysis. It's time consuming. There's a lot of introduction of errors in this process, et cetera. And so, if you can, the best approach is direct introduction sample to the instrument. And so a lot of people say, well, when it comes to especially LCMS, mass dilute and shoot kind of thing, which has some drawbacks itself. But if you can limit that sample preparation, if at all possible, you want to do that. Not always possible. Okay. And I also like to tell my students that there's some things that in academia we just can't model very well that is standard in industry practice. And that is the QA/QC infrastructure behind any measurement that is made in industry, right? Because any number that you generate has to be qualified. It's not only quantified, but it has to be qualified in some way. And so there's this huge QA/QC apparatus surrounding every measurement that is made. And in academia, we just don't have the time or the resources to be able to conduct full-blown QA/QC protocols that industry does. And so it's a real gap between what we can provide in academia and what industry actually does, and it would love to see students with experience with that, or at least some. So, so every time I want to run a sample, it's not just that sample. There's a huge number of standards and controls that I'm running as well to qualify any number associated with that particular sample. Okay, great. In addition to this, now once I've done all my sample preparation, I also need to choose the correct instrument for analysis. And this is just showing that if I want to be quantitative for, let's say, lead in some type of matrix soil or water, well, there are certain EPA regulations associated with how much lead can be in soil and how much lead can be in drinking water, et cetera. And so if I'm looking for lead in those matrices, I want to make sure I'm using an instrument that will allow me to see lead at the concentrations at which it becomes actionable, right? And so I think it's 15 parts per billion lead in drinking water. So once it gets to 15 parts per billion, it becomes actionable, right? There's an enforcement limit right there. And so remediation efforts have to be undertaken to minimize or to reduce the lead concentration below that value. I think it's 5 ppm in the soil. But anyway, so, for some standard atomic spectroscopies that are used for the analysis of lead, there's flame AA, which is very common. It's not an expensive instrument. So many labs have them, but it has some drawbacks associated, which we'll explain a little bit later. And in this case, if you're looking for a metal like lead below part per million level, flame AA can't see it. So it is sensitive to lead. You can't optimize for the analysis of lead, but if the lead concentration dips below about 1 ppm, the instrument's going to say it's not there. Well, 1 ppm is significantly higher than the actionable limit at 15 part per billion. So lead could be there at 15 part per billion, it could be there at 1 part per billion, it could be there at 100 parts per billion, but your instrument says it's not there, right? And so it could be well above what would be considered toxic or unsafe levels, but your instrument said it's not even there. It's zero. It's not detected. And so we have to be careful about the instrumentation that we're using and make sure that it will provide us with the limits of detection and quantitation that we're hoping to achieve. And this is a real issue here as we'll get to see your methods of quantitation. So we're going to be exploring 3 methods here for quantifying an analyte or a set of analytes. So the calibration curve method is known as an external calibration. Most students are familiar with this. You're making a series of standards in different volumetric flasks. You're going to put each of those solutions into the instrument, and you're going to record the response with respect to that analyte. So you have a set of standards whose concentrations of the analyte you're going to plot that on the x-axis, and then the response to each of those concentrations on the y-axis, and you're going to get the curve. And so that's an external calibration because the standards that you're putting into the instrument to develop that relationship response to concentration are external, independent of the actual sample itself. And then we have 2 internal calibration methods where we're actually going to spike the sample of interest that contains the analyte of interest with either a known volume of a known concentration of the analyte itself or of a completely different chemical species and use that method to quantify. And so we're going to look at the advantages and disadvantages of each. So first, the calibration curve method, the external calibration. So in this, remember, we're going to make a blank solution that contains no analyte, so we can get some baseline reading in our instrument. And we're going to subtract that value. We can subtract that value from every other value that we measure. And then we're going to make a series of standard solutions that contain the analyte or analytes of interest and put them in the instrument and essentially measure the response relative to the concentration. Now, the basic assumption of this is that the relationship between the signal and concentration for the calibration standards also applies to any sample that is analyzed. So we're going to find out that this is actually never the case. But that's what it's based on, that that the analyte in every single sample that's put in that instrument behaves exactly the same way in that instrument. That there's a linear relationship doesn't actually have to be. It's desirable that there's a linear relationship between signal and concentration, but we can certainly work in what's called the dynamic range, which we'll see in just a minute. And also that any unknown that we put into that instrument, its response must fall between the lowest concentration standard solution and the response of the highest concentration standard solution that we make. We can't extrapolate beyond the lowest concentration or the highest concentration. Okay, so here's an example curve right here of data where we're analyzing quinine via fluorescence. So it was excited at 360 and emitting at 430, and so we made 6 different solutions right here. And we can see there's some noticeable curvature in here. And so we would call this the dynamic range of response. So what we see here is that every concentration has a unique signal associated with it, but there is a curved relationship between concentration and signal. Okay, so we can be quantitative in this region. All we need to do is solve for x. So if we're given, put an unknown in there, get the y value, the signal, and then solve for x, but that's a little bit cumbersome because it's a polynomial expression, but it can be done. I also want to point out that in any of these figures that we use, the independent variable is always on the x-axis. And what we do is in the instrument is we measure the response to the change in the independent variable. So the independent variable here is concentration. So as I change the concentration, going from one standard solution to the next, I'm looking at the response to that change in that independent variable. So the y-axis is the dependent variable, the response of the system to that change in the independent variable, in this case concentration. And we also want to point out that as analytical chemists, we're dealing typically at trace level concentrations of analytes that are of interest. And so, we use a variety of different concentration units that give us essentially something close to integer values for concentration, rather than using the scientific notation, et cetera. We need to use values that are approach integer values. And then, of course, the signal can be absorbance, emission, intensity, current, whatever method I'm using to detect it. Okay, so this is then a dynamic response. We're looking at the dynamic response. And so here I would specify that my dynamic response falls from 1 to 40 ppm of quinine. Okay, it may actually extend out a little bit higher concentration. I don't know. I don't have a higher concentration. It may go to lower concentrations. I don't know. I don't have a lower concentration. But I can also see here, as you can see with the orange dots, or the orange data points, that there's a region here that tends to be linear. It appears that there's a linear response, right? That signal is linearly related to concentration. And so this is what I have here. So what I show is that blue curve right there is essentially fitting a linear least squares best fit line to all the data points. And what I want to point out here is that why would we do that, right? The relationship is obviously curved. If I take into account all of the data out to 40 ppm, there's obviously a nonlinear relationship between signal and concentration, taking into account all the data. So I would never, ever fit it with all that data with a linear least squares best fit line. Use a polynomial, not a linear least squares best fit line. Now, if you want to focus solely on the linear range of response, the linear range of response is out to 20 ppm. And so how do I know this? Right? So maybe if I had a few more data points, I might extend it to 25 ppm. I don't know. The goal here, when you're trying to decide where is the linear range, which is embedded within the dynamic range. Okay, so the linear range, the dynamic range encompasses both the linear region of linear range of response, and then also a nonlinear range of response. But every response is unique to each concentration. Okay. So how do you decide what is the linear range of response? Well, the number one criteria is keep as many data points as possible, okay, without sacrificing R squared. We don't just choose two data points, because that would give me an R squared of 1. Right? It's essentially a straight line between them. So you keep as many data points as possible without unduly sacrificing R squared. And that takes maybe a little bit of experience, and so we play with that in workshop questions, etc., and how best to decide what is the data point to begin cutting off or to exclude from the linear range of response. So in this case, it's pretty obvious that from essentially 1 to 20 ppm, we obviously have a nice linear relationship. And then if we include the 40 ppm data point, then we need to fit the entire data set to a polynomial. So, okay, I never fit curved data that shows curvature with a linear least-squares expert when we're trying to do quantitation. Okay, so I have an example here that shows a severe limitation associated with this external calibration method. So I'm using an instrument, a flame AA, in this case, flame atomic absorption instrument, to measure the calcium content in 4 different water samples. And these water samples not only contain calcium, all the same concentration of calcium, 50 ppm, but different matrix modifiers. So 2 solutions contain phosphate of different concentrations, 2 contain EDTA, 1 that has both EDTA and phosphate in it. So they're all 4 solutions contain 50 ppm calcium. So I might expect, or should expect, that I'll get the same signal, right? If I'm, no matter where I am here, I should see that if I have 50 ppm, I should have the same signal on this, right? That's what my standards tell me on this for external calibration. But what I find is that I don't. That each of these solutions gives me a different absorbance value or signal associated with calcium. Now, how can that be? They all have the same calcium concentration. I should get the same response on my instrument. Well, we can tell that the only difference between these would be the other components that are within that system. So they must in some way be impacting my ability to detect calcium, to detect and quantify. Okay, well, why is that? So the inherent assumption, as we said before, is that the analyte in my sample behaves identically to the analyte in the calibration standards. And that is never the case. So here's the example data that I pulled this from, etc. And so let's look at this here. So this is the instrument that was used to generate the data here. So to the left, you'll see some lamps that are sticking in. There's some wires going into these lamps. These are hollow cathode lamps. And those hollow cathode lamps, what they're doing is emitting photons associated with the transition of excited state calcium, relaxing back, essentially decaying back to the ground state configuration. So we're looking at calcium ground state, calcium excited state. And so we've essentially excited the calcium within that lamp. And so it's in the gas phase, in excited state, and it decays back down to the ground state and releases a photon. Okay, and so there are photons being emitted by these lamps that are associated with that transition, the energy of that transition. Right. So where you see that plastic bottle, and there's a little tube coming out right there. Well, that tube is connected to essentially a slot burner. There's a flame right there, and that flame is, we're going to introduce our sample in that flame. So that little tubing that comes out right there, we're going to stick into our sample. And what it's going to do is suck up, essentially sample into that flame, right? We have a flame, flames essentially create a sucking action, right? Air movement, air moves towards that flame, and so it creates a little sucking action in that tube. And so we're going to essentially aspirate sample up into that flame. And so that flame then is going to perform some magic for us. I guess we'll explain this in just a second. So first, my sample, if I'm putting stream water in there, an aqueous sample, whatever, my sample is actually calcium 2 plus, right? It's calcium 2 plus that's in there. It's not atomic calcium. But the photons coming out of that lamp are associated with a transition between excited state and ground state atomic calcium. Okay, well, atomic calcium and calcium 2 plus are completely different chemical species, right? Chemistry is an electronic process, and so chemical species that have different numbers of electrons have different chemical properties, right? This is what you learn in general chemistry. As you go down a group, all those chemicals have the same number of valence electrons. They may be in different shells, but they have the same valence electron, right, different orbitals. So they have the same number of electrons, so they have very similar chemical properties within a given group, right? But this group, adjacent to this group, they have completely different chemical properties because they have different numbers of valence electrons. So calcium, atomic calcium, and calcium 2 plus are completely different chemical species. In fact, calcium 2 plus and magnesium 2 plus are more similar than calcium 2 plus is to calcium in terms of the chemistries. Right, so sending a photon into a solution that contains calcium 2 plus, a photon associated with the atomic calcium transition from the ground to the first excited state, that does nothing. Calcium 2 plus doesn't see that photon, doesn't interact with it because calcium 2 plus is not atomic calcium. So that means I have to convert calcium 2 plus to atomic calcium so that it will absorb that photon, right? Because that photon has the energy necessary to take that ground state atomic calcium up to the first excited state, right? And if it absorbs that photon doesn't hit the detector, and therefore I see a smaller signal. Fewer photons hitting it, but which if we transform it essentially gives me a larger absorbing signal. Okay, so that means I have to convert calcium 2 plus in my sample to atomic calcium, and that's what the flame is for. So the flame has a couple of jobs to do. First, it has to remove any ligands that are surrounding the metal of interest, in this case, calcium 2 plus. Okay? And in my samples, the ligands of interest are phosphate and EDTA. They're both very good complexing ligands with respect to metals and calcium 2 plus in particular. And so calcium 2 plus exists as the solvated calcium 2 plus in that solution. There's some calcium with water molecules around it. There's calcium with phosphate molecules around it, and there's calcium with surrounded by EDTA. You can say multiple EDTA molecules because it's a chelating agent, but it's complex to each of those in solution. And so the flame has to remove those ligands before it can actually atomize the calcium 2 plus. So remember, in a flame, in this case, we're burning acetylene, we're oxidizing acetylene. So there's a lot of free electrons in that flame. And so once I remove those ligands, those free electrons are highly reactive. They're essentially going to reduce calcium 2 plus to atomic calcium in that flame. So the flame has a lot of work to do. We're asking a lot from this flame. It has to be able to break those metal ligand bonds and then atomize that calcium so that the calcium rods in that flame can absorb the photons that will be essentially directed toward through that flame. Okay, and then the more successful I'm at doing that, and the more calcium there is, the more photons are absorbed, and so I get larger absorbance signals. Okay, so it's asking a lot. And so what happens here is that EDTA is a very good complexing agent. It grabs calcium and can actually outcompete phosphate for the calcium. So any solution that contains EDTA is calcium is highly complex to that. But in the flame, EDTA is a weakling. It's an organic molecule and essentially falls apart. And so it's easy for that flame to break the calcium EDTA bonds. And that thus exposes the calcium 2 plus, so it can be atomized and then absorb the photon. And so when that happens, I get large signals. So any solution that contains EDTA, I get a fairly large signal because it's a fairly efficient process to break those metal ligand bonds. But those solutions that contain phosphate, not so good, right? Calcium phosphate bonds are thermally stable, highly thermally stable. My air acetylene flame is not hot enough to essentially be efficient at breaking those bonds. So if I'm not efficient at breaking those bonds, I'm never going to atomize the calcium, so I'm going to get a reduced signal. So my instrument will think, right, that there's less calcium than there actually is, and therefore I see smaller signals. And so as the concentration of phosphate increases, I have smaller and smaller signals. Okay, and this is just the setup of the instrument right here. We have the light source, the high cap, the lamp, the flame. I put a blank in there to find out how much light is hitting that detector in the absence of any calcium. Then put my samples in there. P is smaller than P0 because less light's hitting that detector because it's being absorbed, and the ratio of minus log of that ratio, P over P0, is what we call absorbance, which we'll address in the subsequent lecture. So this is how the measurement's being made. But the thing is that the matrix that the analyte is in determines really the quality of the data that I'm going to get. All of these essentially give me 50 ppm calcium. I should get the same signal. But because the method I'm using suffers from severe matrix effects, the flame is not hot enough to break those metal-laden bonds, I get reduced signal. So I think that there's less calcium in there than there actually is. Okay? And this is a severe limitation. Matrix effects are a severe limitation of calibration curve method because there's no guarantee the analyte in your sample will behave identically to the analyte in your standards that you're making in the lab. And so this is a severe limitation. So here's an example here. I have essentially the DI water curve is calcium standard solutions I made in the lab using DI water and nanopure water. Okay, no complexing ligands other than water molecules, which easily are removed from the calcium. So I'm able to essentially get a good signal at every calcium concentration. Then I have a hypothetical stream water here that contains a mixture of different ligands, etc., but no calcium. So I'm making a set of calcium external standards using the stream water. Okay, so I know the calcium concentration, but it has a more complicated matrix than just DI water. Okay, and I see that there's a suppression of the signal because there's phosphate in there, and maybe some other inorganic ligands, and the flame is not very efficient at essentially breaking those bonds so that calcium 2+ can be atomized. So at any given concentration, I see a reduced signal. Okay, so now let's say I grab a real sample, a real stream water sample, and I want to know how much calcium is in that stream water sample. And let's say I measure an absorbance of 0.4. Okay, well, if I use the curve generated by DI water, I get 14.5 ppm. But if I use the curve generated using the stream water-based calibration standards, I get 32.7 ppm. So which one's correct, right? It's whichever one has the matrix most closely similar to the actual sample. In this case, probably the stream water, right? But that's a huge difference in concentration, right? And so this represents a severe limitation to using external calibration methods when it comes to quantifying analytes in given matrices. And so industry will not use external calibration methods for quantitation because of the severe matrix effect. Now, one thing I do want to point out, and it's absolutely crucial that this is so, because the methods we're going to use to actually quantify analytes depend upon this. If I look at this, right, I can see that in both cases, from essentially 1 to 50 ppm, both curves are in a linear range of response. So independent of the matrix, we tend to have that the linear range of response tends to be independent of the matrix. Okay, and get different slopes based on the ability of the method to overcome or how it's impacted by the matrix effects. But no matter what the matrix, we tend to get the same linear range of response with respect to concentration and signal. Okay, and this will become important. But this is good. So as long as we're in the linear range of response, all is great. Okay, so if industry doesn't use the external calibration curve method, that means it must use one of the internal calibration methods or both. And so that means that these must remove the matrix effect. Okay, So if we're going to use these methods to quantify, we have to remove the matrix effects. So the experimental design must be employed in such a way that there is no matrix effect and that we can trust the numbers we're getting to be the true numbers associated with concentration. Now, this method does assume that response is proportional, linearly related to the concentration. So it means we must be in the linear range of response, no ifs, ands, or buts, for this to work. Okay. And there are two methods. They're actually the same. There's what's called the direct addition and dilution to a constant volume. Dilution to constant volume is what we do in lab, and all it is we're doing the experiment multiple times just to make sure we're doing it right. Direct addition means we're doing it once, and who knows, maybe I miscalibrated my micropipette and I don't have the concentration in there that I think I do, and so my signals associated. I associate my signal with a concentration that actually doesn't exist in there because I messed up. I would never know. So if I do it multiple times through this dilution of constant volume, I will know whether I'm relatively, my actions in lab are reproducible. Okay, doesn't mean I have actually a systematic bias, but at least my actions are reproducible. Okay, so what are we doing? Well, this is the fundamental basis for standard addition. We're operating in the linear range of response. Okay, we must be. So we can't be in the dynamic range, we must be in the linear range of response. And if I'm in there, but it says that any ratio of response to concentration is equal to constant. It's a slope, a constant slope. So that y1 over x1 equals y2 over x2. Okay, that's great. So I'm going to design my experiment so that I can solve this mathematical expression. Okay, and that's really all we're going to do is we're going to design an experimental setup, experimental protocol that allows me to solve this equation. Okay, so here's an example. I have a solution of unknown copper. I put in my instrument and I get a response of 2.36 micrograms. Okay, I'm going to make a solution of copper. Doesn't matter that the matrices are different. I don't care what the matrices are at the moment or how different or how similar they are. It doesn't matter. So I'm going to make this standard solution of copper and I know its concentration. No ifs, ands, or buts, I know it. So what I'm going to do is take a large volume, relatively large volume of my unknown solution and place it into a different volumetric class or container. And then I'm going to spike it with a small volume of that known standard solution concentration. Okay. So now if I look at this flask here in the middle, right, its total volume is 25.5 mils. Okay. If I look at that, the matrix associated with that sample is essentially identical to the matrix of the unknown, right? 25 with 25.5 mils comes from that unknown solution. So I've effectively removed the matrix mismatch. They effectively have the same matrices now. So the analyte is really going to behave exactly the same in those two solutions with respect to my instrument. So I'm going to put that into my instrument. I get a 3.79 micrograms. Okay, so I'm going to go back for a second here. This is what we've done. I have my unknown solution y1, right? Put it in there and I get a response. I don't know what x1 is just yet because I don't know the slope. Right? I haven't done external calibration here. And then I've just made a second solution where I'm going to put in the instrument and I've gotten y2. Okay. And then what I need to do then is essentially take the ratio of the responses and that will equal the ratio of the concentrations. So let's take a look at this. y1 over x1 equals y2 over x2. So what I'm going to do is just go y1 over y2. The ratio of the responses equals to the ratio of the concentrations in those two samples. All right, great. So 2.36 micrograms is to 3.79 micrograms. That must be equal to the ratio of the concentrations. And I'm not particularly happy with my subscripts right here with the F in there, but that's okay. So what I'm going to do here is that the concentration of copper in my unknown is unknown. I don't know it. Okay? But in that spiked solution, that 25.5 mil solution where I took 25 mils of the unknown and then spiked it with 0.5 mils of that standard copper solution, right? That has two sources of copper, that spiked solution. Right? So has copper from the unknown, and it also has copper 2 plus from the standard solution, right? And they're additive. It's just like if I have 2 marbles in my left pocket and 3 marbles in my right pocket, and I put them together, I have 5 marbles. They're additive. Same thing. I'm going to take a certain amount of copper from one source and add it to a certain amount of copper from another source, and the total copper is the sum of the two. So all I need to know then is how much copper is from the unknown. Well, I took an initial amount of unknown copper concentration. I took 25 mils of that and diluted it to 25.5 mils. So it's M1V1 equals M2V2. So the concentration of copper in the spike sample from the unknown is just copper 2 plus unknown times 25 mils divided by 25.5. You can see I have liters in there. That's okay. And then I have some copper in there from the standard solution, right? And that standard solution is essentially taking its concentration, M1, times the volume, which is 0.5 mils, and divided by the total volume that it was diluted to, 25.5. That's 0.006. So you can see now I have a single equation and a single unknown. So all I have to do is solve for copper 2 plus initial, and that tells me what the concentration of copper is in the original flask. Okay? And so I get 9 times 10 minus 4 molar. That's great. And so this method, right, the experimental design is solely designed around solving y1 over x1 equals y2 over x2, which we transform into the ratio response to ratio concentration. That's how it's set up to solve that expression, okay? And it does so by essentially taking our unknown solution, putting in the instrument, and then taking some volume of that and spiking it with a solution of the analyte of interest, whose concentration is known. And so all of it is essentially designed around solving y1 over y2 plus x1 over x2 and minimizing the matrix mismatch between the two samples that we're putting into the instrument. Beautiful. So let's take a look at this particular problem right here. So the iron in aqueous sample is determined by pipetting 10 mils of an unknown into a 50 ml volumetric flask, adding 10 mils of a standard containing 12.2 ppm E, and diluting the marker water. Now in this particular case, our signal is percent transmittance, and I'm just going to say right out that we have to convert these percent transmittance values to absorbance values because transmittance and concentration are not linearly related, which is why we take these values, these transmittance values, and convert them to absorbance. And that's essentially a topic we discuss in spectroscopy, which will be the next lecture on PowerPoint, etc. So that's one of the first things we have to do. Okay, so here we are. I have my unknown iron 3 plus solution, okay? And I have my standard solution of iron 3 plus that I made, 12.2 ppm. I'm going to take 10 mils of my unknown and put it into a volumetric flask, and 10 mils of my standard solution and put it in there. I do want to point out, this does not remove the matrix effects, right? Because the matrix of that spike solution is different than the original unknown. So this kind of the standard addition method, the example here, is not removing any matrix effects. But what we're trying to do is work through the workflow and how that translates to math we're trying to solve. Okay, so even though we're not removing a matrix effect, we are essentially building up our skills at essentially developing these workflows and how they help us solve in math. Okay. Okay, now we did dilute to 50 mils right there by adding 30 mils of water. Okay, so I've converted my percent transmittance values to absorbance values here just by taking the minus log of 0.6295 and the minus log of 0.5105. We don't take the minus log of percent transmittance, we take the minus log of transmittance. Okay, so again, we're just solving y1 over y2 plus x1 over x2, which is 0.201 over 0.292. And so the concentration in the original unknown solution is X. In the spike solution has two contributions. I took 10 mils of the unknown concentration diluted to 50. And then I took 10 mils of the known 12.2 ppm solution and to 50 mils. And so I can solve for X. And the iron 3 plus concentration is 1.9. Now recall this, now I'm not doing this in lecture. We're having students go through these calculations until we reach some type of class consensus of what the answer is. And of course, we go around and help students to set up essentially the workflow and the corresponding equation and come up with the answer. So we're doing this much slower in lecture. So another example in lecture right here, I'm going to go right through real quick here. Okay, so this is a little bit more complicated right here to show because we're building up to more complicated methods or protocols right here because the workshop questions are more difficult than what I'm showing right here. So we just want to give students from slowly building up into slightly more complex ones. So I have an initial quinine solution that I've made where I dissolved a tablet in 1 liter 0.1 molar HCl. That's the upper left-hand flask. So presumably the quinine concentration is too concentrated. So what I do is I take 20 mils of that, put it into a volumetric flask and dilute it to 100 mils. Then I put that into my instrument and I get a signal of 540. So there's an extra step in there. Okay? And so they have to be able to figure this out through the workflow. So the two flasks that are put in there, the diluted quinine solution and then the spiked quinine solution. Okay. And so you can see that in the numerator there's a M1V1 equals M2V2 term that wasn't in the prior examples that we had because we had to do that dilution step. Okay, so it's been up here long enough that you can pause it or whatever so you can look through the calculation yourself. Okay, so another one right here, sample coffee is analyzed to determine caffeine concentration. So this is the workflow. Again, we have an initial dilution step here. Where we've taken 50 mils of it and diluted it into a total of 60 mils and put that 60 mil diluted solution into the instrument. Okay, so again, the same setup right here, and this is the concentration that we obtain. Okay, so this is probably our basic protocol that we're using, trying to get students facility writing up these little workflows right here, because once you have that, then the mathematical expression really falls out. Okay. All right, great. So that's standard edition. And so then the workshops are essentially going to tweak that a little bit more and offer some slightly more challenging questions or protocols that we've used. All right. So many times though, right? So in the cases I've shown here, I'm looking for a single analyte. I'm looking for quinine, I'm looking for iron, looking for copper. Well, lots of times, especially in environmental analysis or if we're doing blood analysis, things like that, we're looking for huge numbers of simultaneously, right? And so we're using chromatographic methods because we have to separate out the components of the mixture so we can probe them independently. But the goal here is to, within a single experiment, quantify, right, all the analytes that are present. So it's pretty difficult then to have standard solutions for all these different analytes, right? Even a single solution that contains all the analytes of known concentration, that's a lot to ask. And so instead, this is just an example of some blood analysis for animals by the veterinary medical diagnostic lab at Texas A&M, just showing that they're simultaneously looking for many different analytes within a given experimental protocol. So rather than make a solution, standard solutions that contain all those analytes, right, or a single standard solution that contains all of them known concentration, which is quite a bit, we're going to do something a little bit differently. So again, this is actually from a consulting project that we were working on a while back, where we developed an LCMS method for quantifying the three heat-related chemicals associated with peppers, right? Capsaicin, dihydrocapsaicin, dihydrocapsaicin. These are the capsaicin compounds that essentially give peppers their heat. And there are other compounds as well that don't really contribute to the heat. So in this, you can see there's sertraline. Sertraline is an antidepressant, and but that is what we were using. We added that to the sample as a means to quantify the amount of capsaicin compounds. So that's pretty strange. Why would we add sertraline? Well, we did it because we knew that sertraline didn't exist in the actual samples that we were looking at. We don't expect to see this antidepressant in food extract, hopefully, at least for the food extracts that we were looking at. But it has properties very similar to the compounds that we're looking for. And that's the basis of this internal standard method, which is the second internal calibration method, known as internal standard. So there's two internal calibration methods, standard addition and internal standard, okay? So in this case, we're going to add a chemical species that we do not expect to see in our actual sample, okay, but has properties similar to that of the analytes of interest. And that can be a tall order. So the purpose of the internal standards is to improve precision of the estimate of the analyte concentration. And part of this, what it's saying is that, every method has random error associated with it, especially for dealing with mass spec and flames and everything. And so what happens to the analyte, right, its signal can bounce around from one injection to the next. But if I had an internal standard that behaves very similarly, so will it, right? Its signal will bounce around as well, but the ratio of those two will always be the same, because if this one in one instant increases, so will this one, okay, because it will respond similarly to the instrument, right? So that ratio remains constant. So they can both do this, but the ratio will be relatively constant. And that's the goal right there. Okay, so the ratio of the two signals will exhibit less variability than the actual signal itself, the analyte signal. But we can also use it to quantify that analyte. Okay, so here it is. Again, we're operating the linear range of response for both the internal standard and any analyte or analytes of interest. Okay, we must be operating in linear range of response. Okay, and so these equations here are still just y1 over x1 equals y2 over x2. They're the same thing, right? That any signal associated with one of the internal standard concentrations is equal to the signal of any other concentration of internal standard as long as we are in the linear range response. I should say the ratio of signal to concentration. And the same thing for our analyte of interest. Okay. So the thing is then, is that the ratio, right, of signal to concentration for the unknown relative to the ratio of the signal of the internal standard to its concentration is equal to constant, because a constant over a constant is a constant. And that will hold true as long as we're in the linear range of response for both the internal standard and the analyte or analytes of interest. And so that constant, the ratio of the ratios, we call a response factor. Okay? And we're going to use this as a means to quantify X, right, the concentration of the analyte of interest and our sample unknown. Okay, and so what has to happen is I have to know what F is. I have to know what this response factor is. My instrument's going to give me the signal for both the analyte and for the internal standard. So I know those two values. The instrument's going to tell me this, right? So I'm going to add my internal standard, a known amount of it. So I'm going to know what the concentration of the internal standard is in my spiked sample. So I know AX1, I know AS1, I know S. So what I have to do is make a standard solution that contains both the internal standard and my analyte to get F. And as long as I'm operating the linear range response, any analyte unknown, any unknown solution, right, F is constant. So if I make a standard solution of both, I'm going to get F. So that way, anytime I put an unknown into there, the only thing I have to solve for is X. So we'll see that in just a second. All right. So in this case, DDT is the analyte of interest, and chloroform is my internal standard. Now, there's a tweak to this that's going to make the method a little bit more complicated, so we're going to follow along. I am making this solution. It's a solution that contains both chloroform and DDT. I know the concentration of chloroform, I know the concentration of DDT. I put them in my instrument and I get their respective responses. Okay, so I can calculate F, right? The signal associated with DDT relative to its concentration over the signal of the internal standard relative to its concentration gives me a response factor of 0.413. Okay, so now all I'm going to do now, I know F. As long as I'm in the linear range response for both these analytes, for the internal standard of the analyte, F is a constant. It's 0.413. So I'm going to design my experiment such that I measure AX and AS, okay? And I'm going to design it such that I know S. So the only thing I have to solve for is X. So here we go. Here's my unknown DDT solution. I'm going to take 10 mils of that and put it into another flask. And to that, I'm going to spike in a known volume of a known concentration of my internal standard. again, look at the ratios here. 10 mils of unknown to 10 microliters of my internal standard. So the matrix of the spiked sample is essentially identical to the matrix of the unknown DDT sample. So I've removed the matrix effect. Okay, all right. So total volume in my spike solution is 10.01 mils. So I'm going to put that into my instrument, and I get a signal for both DDT and chloroform. Okay. So before we go to the next one, I'm just going to summarize all this information. The concentration of chloroform in my spiked 10.01 mil solution is 12.5 millimolar. And I determine that by the volume I spiked, 10 times 10 minus 3 mils, or 10 microliters, times the density of chloroform, divided by the molecular weight of chloroform, divided by the dilution factor. And that dilution factor is really 10.01, but 10.01 and 10 are so close, I just kept it at 10. So the concentration of my internal standard in that spike solution is 12.5 millimolar. So here's the summary of the information from the last slide. All I have to do is solve for this, right? So I have the two signals, my instrument measured that. I know that the solution is 12.5 millimolar. I see I have a 12.6 there, sorry. And I know F. So the only thing I have to solve for is X. And so that's 8.96 millimolar. That is in the spiked solution. That's what I put into the instrument. Remember. So remember that the DDT in the original sample, right? I took 10 mils of that and diluted 10.01. So there's an M1V1 equals M2V2 that I have to back calculate the original concentration. Like 10 mils versus 10.01 mils, those are so close that I just say that it's essentially a constant. It's 8.96 millimolar in the original solution. I know I added a tweak to that, so think about it and make sure you agree that by essentially saying 10.01 and 10 were essentially identical, I made these approximations, okay? And I assume I'm justified. Okay, another one. So we have an internal standard method here, iota acetone. I'm actually going, you can pause it right here, okay? I'm not going to go through this in great detail. I'm just going to pause here for a second, give you a chance to pause, hit the pause button and write this down if you want, okay? And so here's a summary of the information on the prior slide, okay? So remember, that's a solution I made of iota acetone and p-dichlorobenzene. I know the concentration of both. I put them in the instrument to get a signal for both so I can calculate my response factor. Now I'm going to essentially take a solution of iota acetone and spike it with p-dichlorobenzene. Okay, put that in the instrument, and essentially I'm going to get 1.22 times 10 minus 7 molar. But based on that protocol, there was an M1V1 equals M2V2 that I cannot ignore now. And so because I diluted that, the actual spike sample is the diluted sample. So now I have to back calculate what the original concentration is in the original solution. All right, again, you can pause this and follow the math as you want. I'm going to continue on because we're dragging on here. Okay, so one more method right here. Just pause for a second so they give you a chance to hit the pause button so you can follow the math right there. Again, all these we work through in class, and we write the solutions up on the board as we go along, and we make sure we have consensus among the students in the class. Okay, finally, this is the last slide. What I want to point out is how we perform this internal standard method in the prior examples is not the full picture. Okay, so couple things we need to do. We need to prove we're in the linear range of response to use the internal standard method. And so the experimental protocols will be designed to do that. Simultaneously calculate the response factor and the concentration of the unknown and unknown, but also at the same time prove in the linear range of response. So I have 4 solutions right here, 4 vials. They were put into a GC, they're made directly in a GC vial. Vial 1 contains 10 ppm of cyprodinol and 10 ppm of imidacloprid. These are pesticides. Okay, so I made the sample. I know the concentration of these 2 analytes of interest. And I know the concentration of the internal standard anthracene that I put in the vial. Okay, so in vials 1, 2, and 3, I know the concentrations that I made these. Okay, so the sole purpose of these, well, there's two purposes. One, if you look down below at the table, that blue highlight right there, that blue circle, highlights that one, that's just external calibration curve data. So I have 3 vials, 10, 20, and 30 ppm with subprodinol, and I have the signal associated with subprodinol. So I can plot up that data and prove, hopefully, that I'm in the linear range of response for subprodinol. I can also do the same thing for imidacloprid because those vials contain 10, 20, and 30 ppm of imidacloprid, and I have the corresponding signal for imidacloprid. So I can plot the external calibration curve for imidacloprid to show that I'm in the linear range response. Okay. All right. I also want to point out that in every one of these, and this is typically how it's done, is that the internal standard is always spiked in, so its concentration is the same. It's always the same in every standard solution I make, as well as the unknown. Okay? It's just the way it's done. No reasons, but it's the way it's done. Okay, so now I've proven I'm in the external range of response, which I'm not going to show you the figures. We're not running out of time, but I do show that in class. So we're in the linear range of response for both of these amyloids. So now what I can do is I can calculate the response factor. So for that 10 ppm vial, I have 10 ppm subprodinol, 10 ppm anthracene. I have the signal for subprodinol and the signal for anthracene. So I can calculate the response factor for the subprodinol internal standard pair. Okay. I can do it again at 20 ppm. I can do it again at 30 ppm. I'm going to get 3 F values. I'm going to take the average of those 3 and use that average response factor to calculate the subprodinol concentration and the unknown extract. Okay, I can do the same thing for imidacloprid. The 10 ppm vial has 10 ppm of imidacloprid, 10 ppm anthracene. I have the signal for both imidacloprid and anthracene. I can calculate the response factor for the imidacloprid anthracene pair. And I can do that 3 times and take an average of those 3, and then use that average response factor to calculate the imidacloprid concentration and the unknown extract. That's how we're going to do it. This way we get multiple response factors. I can take an average, right, and then apply that to whatever unknowns that I'm running. So this is how it's really set up, right? And of course, in industry, they're going to be running many more standards and many more samples simultaneously, et cetera. So they get good statistics on here and stuff like that. Okay, so great. Save. All right, so I apologize for taking so long, but that is essentially the methods of quantitation, which I'd say is normally 2 to 3 lectures long, 3 lectures long. This PowerPoint usually takes about 2 lectures to get through, and then we have an extra lecture where we actually just work on nothing but problems throughout the entire lecture. And so I did this all in one shot, so it's a long one. I apologize for that. The next video is going to be essentially an introduction to spectroscopy. Okay, so hopefully I'll see you then. Take care.